Welcome, everybody, and thank you very much for the kind introduction, Raul. Also, thank you to all the team that organizes the UQ seminar for inviting me and giving me the opportunity to talk here. So today I will talk to you about, as Raul said, stochastic gradient with least squares control variates. So it's a talk on optimization, and this is joint work with my advisor Fabio Nobile and Nathan Scheffer. So this is the outline of my talk. First, I will be introducing and setting up the problem. Then I will be talking to you about what are control variates and how to use memory to build control variates. And then be going into weighted least squares. Then I'll be presenting our algorithm, the SGLSCV, so the stochastic gradient least squares control variates. Then I'll present some numerical experiments, and finally leave you with some conclusions and outlook. So let's start with the problem setup. Right, so what is the kind of problem that we are interested in? This is a standard stochastic optimization setup. So we wish to solve, meaning minimize a functional j, which depends on some design or control. I will call EU the design or control from now on, which is given as an expectation over some random parameters, which is here denoted by, which they are denoted by y with some law rho. And so the function is just an expectation of some function g, which depends on the design and the parameter, and the search space we assume to be a Hilbert space. So we're in an unconstrained minimization setting. The thing that we assume is that this G is a costly model, right? So we assume that this probably evaluating G also entails solving some complex PDE, which means that evaluating G and the gradient of G is expensive. So in our minimization from now on, our objective will be really the one to minimize the number of calls to this function. And we work also in the kind of nicest possible setting, which is one where G is C1 and in the gradient. So whenever I take gradients here of G, it's always gradients with respect to the design U. It's never with respect to Y. So that's why I just use a generic Nabla operator without the subscript U. So this is the gradient of G with respect to U is L Lipschitz in U in this as explained here with a Lipschitz constant, which is integrable, a square integrable. And also we assume that J be alpha strongly convex. So this is really like a nice setting that we are considering. Now, since it's a very nice setting, as I said, also like a very simple algorithm in principle could work, right? So everybody I think is familiar with gradient descent, where the update rule for gradient descent is just update the kind of the current design UK with a step in the direction of the gradient with some constant step size, and with the current assumptions, if we take the step size small enough, then we have that the error of the iterates decreases exponentially, right, with the rate, which is the one here. And you can see in this plot, actually, we have very, very fast convergence of this algorithm. So think of this kind of gradient descent in our setting kind of as our baseline, right? This is like kind of the ideal algorithm we would like to have. The problem that I say it's ideal, it's the following. So here the bottleneck is that taking the gradient of J is actually the expectation of the gradient of G, meaning that this requires, so either one has this kind of expectation in closed form, but in general, this actually requires the estimation of this expectation, the discretization of it. And for instance, a Monte Carlo with many samples per step is too expensive because remember, we are considering a setting where evaluating the gradient of G is expensive. And so you see that if I plot now, the same plot is earlier, but I plot versus instead of versus number of iterations, I plot versus number of gradient evaluations, the curve changes drastically, right? So what people do normally in this setting to kind of reduce the cost is the following, which is doing stochastic gradient descent, which is another algorithm that I trust the audience is familiar with, but let's just go through it together once again. So stochastic gradient descent has the following update rule. So we take a step in the direction of what's called the stochastic gradient, this grad j hat, which is an unbiased estimate of grad of j. And I mean, there's multiple versions. The kind of standard Robbins-Monroe version is at each iteration we sample one random parameter and we evaluate the gradient of g at that random parameter, and we use that as an estimator, or we can evaluate the gradient of g at multiple random parameters, right? And this is kind of the mini batch way to do it. And so you see now that gradient descent kind of improves, especially at the beginning, the performance of gradient descent, the complexity. So here again, I'm plotting versus number of gradient evaluations. Actually, asymptotically, actually gradient descent would catch up. But so this is an improvement, but it's kind of still not enough because here convergence is achieved by shrinking and killing the variance, so shrinking the step size and killing the variance of the stochastic gradient in this manner. And the convergence rate that we get is 1 over k, which is so this algorithm is very cheap per step, but it only achieves algebraic decay of the error. So now the question is, can we do better than that and improve convergence, perhaps exploiting the history of the gradient evaluations? And this is kind of a question which has been tackled, I would say, in the last 10 to 15 years by multiple works. And among them, I would like to, I mean, kind of the most relevant for our work is this SAGA, which is this work from 2014 by the Fatsuebach and Lacoste-Julien. And the idea of SAGA is really to do variance reduction of the stochastic gradient by exploiting the history of the gradient evaluations. So actually, SAGA is native for what I call finite sums. So functionals j of u, which are given as a finite sum. So there's only a finite number of kind of parameter values. So we could think we can think of it as having like rho as a discrete measure over a finite set of points. And so, as I said, the idea of SAGA is to store past component gradients as a control variate, and the algorithm goes like this. So you initialize at some design, and then you initialize the memory, which is size S, and for each iterations, just like in kind of a stochastic gradient, you pick randomly one, uniformly random one index jk, then you compute the gradient at the current design and at that parameter y of jk. And then this is the update. So this is where the control variate comes in. So the update is the gradient of g, the gradient that we just computed minus our kind of best approximation in our memory of this gradient, which is this psi, and plus then the average of the gradients in the memory. And the remarkable thing is that this this algorithm achieves an exponential convergence rate in the strongly convex case with one essentially O of one gradient evaluation per iteration. And so you see that the picture essentially is much improved. However, on the contrary, the cons are that the memory, first of all, we have a memory constraint because you see that if we have many terms in the sum above here, then we need to have a memory that scales with the number of terms in the sum. And also the rate of convergence degrades as S grows. So here I have like as S grows, you see how the convergence rates, it's always exponential, but decaying pretty rapidly. And kind of this is a byproduct of the fact that this method is not native for a continuous probability measure, which and continuous probability measures arise all the time, like in problems that we care about. For instance, in PDE-constrained optimization, those problems really kind of are written in the setting of a continuous probability measure over the parameter space. So now, what do we want, right? So we wish, of course, to improve on this kind of limitations that SAGA has, but we would like to still keep the kind of favorable kind of SGD or SAGA kind of cost per iteration where we do either one or just a few valuations. And we also want to, kind of follow this idea present in SAGA and many other works, which is kind of the exploitation of the history of the optimization to kind of improve convergence, right? So, and the kind of the key observation is the following. So, in problems that we care about, so the picture actually looks kind of like this. So here I'm plotting, so the parameter is on the x-axis, which is now a y, and what I'm plotting in blue is the true, at our current design, the gradient of g as a function of the parameter. So um, we see that, so sorry, and then in red, I have some past evaluations of the gradient at some past designs, right? So these are evaluations from UK, but if UK minus I is close to UK, then we could say that, okay, these are inexact evaluations, but the error should be kind of small. Also given the Lipschitz property of the gradient that we assume. And so this is the kind of the picture. We have a very smooth gradient and some evaluate like some observations of it. And so the idea is that, well, in SAGA, we would just predict kind of the value as the red points for the blue curve. But our idea is very simple, since we say so. Since in many applications that we care about, actually there's some smoothness, right, of this gradient grad of g UK comma y. Then what we can essentially fit a control variate that generalizes over the parameter value. So very simple idea. Right, so our idea is to reuse the history to learn a control variate, which I call now VK of Y, which should be kind of like the gradient of approximating the gradient of G. And this has to generalize across Y. And then we want to use it to reduce the variance of the stochastic gradient update, just like SAGA does. So more formally now, let me introduce what we call memory-based control variates, which is kind of a generalization of SAGA which works actually for discrete and continuous random variables y. And so we let the model VK be a function from the parameter space gamma to u. And this is a model for the gradient of g at iteration k. So this is what I just showed you in the earlier slide. And this is constructed using the previous SK gradient evaluations. So we assume that we have this kind of sequence SK, which determines how far in the past we're looking. And then kind of this model at this level could be anything. Think of a regression model, a kernel interpolation, a Gaussian process. So we're really not, I mean, the kind of only constraint that we have in the choice of this VK at this level is that is the following. So we have to have this property where computing the true expectation over the parameters of this model has to be cheap and we have to be able to do it exactly. So so that's kind of the only constraint at this level on the kind of model class that we can choose. And then let me introduce this memory term. So this calligraphic SK, which is essentially the memory, the data sets that we use to fit this model to the grain of G. And I mean, in this case, again, V0 as 0 could be initialized. I didn't say it, but this is kind of also a question in SAGA. How do you initialize the memory? There are multiple ways. For instance, one is to do like just a few SGD iterations. So now, what is our algorithm? So this is kind of the most general algorithm that we propose, and it really follows closely SAGA, as I showed you earlier. So after we have an initial guess, initial model, initial memory, for each iteration, we just draw one parameter according to our distribution rho, independent of fk. This is the past, this is the sigma algebra of the draws up until and including yk minus 1. And we compute this one gradient at G. And then, just like in SAGA, we update with this rule, essentially where we take the newly computed gradient, we subtract our prediction with the current model, and then we add the expectation over model. And this is, I mean, if you're familiar with control variates, this is exactly a control variate kind of approach. Then we update the memory. This is dictated by our sequence small sk. So that tells us how far into the future we have to look. Sorry, into the past. Then we update the model using the new memory. Right, and note that this grad j hat is still a conditionally unbiased estimator. This is trivial because, I mean, if you take expectation, just these two terms cancel. Right. So now the point is of all this is that we are fitting a model. So in order to be more general, sometimes it's actually good when one just I mean builds a regressor. It's more convenient to sample the parameters from a sample kind of a different sampling measure than the base measure rho. And so here we want to kind of generalize the algorithm that I just gave you to an important sampling setting, which is the following. So which is the one where instead of drawing samples from rho, we draw samples from mu. And really, the update is almost the same. The only thing that needs to change is that we have to kind of adjust, kind of reweight our update by this kind of likelihood ratio. So d rho over d mu, but the rest is kind of all the same, right? So now we can accommodate also sampling from a different measure. But what we would like to do is actually do it even a little more complex, meaning that we would like to accommodate the case where the sampling measure actually depends on the iteration, right? This could be because this model that we're fitting, maybe we take it from different like over the iterations, we may take this model from different spaces, right? And if the kind of modeling space changes also reasonably, maybe we would like to change the sampling measure. So in order to be as general as possible, we also designed the algorithm to work in this setting. So what has to change in this setting? So the point is that at step k plus 1, all the evaluations in the memory should be at parameters drawn from mu k plus 1. And clearly, if we just repeat the previous algorithm, this wouldn't be the case because then kind of the previous the previous evaluation would be from mu k, the second to last would be from mu k minus 1, and so we essentially would have an heterogeneous memory. So what we need to do is at each iteration we need to kind of correct the memory to keep it consistent, right? So we can do this by a resampling step. And so what we do is suppose we can write the measure at step k plus 1 as a mixture of the old measure mu k plus a new measure eta k with so this with a parameter alpha k in 0, 1. And the and so the resampling step is the following. So we initialize the memory as is, as it's given to us by the previous step. And then we do kind of a sweep over all the elements in the memory, and we draw a Bernoulli according to alpha k. And if the Bernoulli is 0, we essentially redraw that that observation. Essentially, we re-evaluate at that. So we draw a sample y tilde j from the new measure eta k, and we replace the old evaluation with a new one in sk plus 1. And so after the sweep is done, our resampling step is done. And note that the expected extra cost per iteration, of course, we incur in an extra cost, is 1 minus alpha k times the size of the kind of the input memory. But the observation here is that if alpha k is close to 1, meaning that kind of mu k plus 1 and mu k are almost the same, but for a kind of a very small perturbation, then this kind of extra cost per evaluations remains constant and kind of is negligible. So now that now that we have the resampling step, how does the algorithm change? And it's really similar to what we had earlier. So now we draw the yk, we draw it from uk. We again have the important sampling so weight in our updates as we had earlier. Then what we do is again we update the memory. Then we have also to update the sampling measure and then resample the memory. And finally, we update the model at step vk plus 1 using the resampled memory, which is now with observations drawn from from distribution μk plus 1. And you see that if you, like by induction, if you do this at each step, actually, you do get a consistent memory at each iteration. Okay, so now we're ready we've been going on I've been going on about this model, and now I would like to introduce what kind of models do we use and what is the fitting procedure that we propose. And spoilers, this is going to be with least squares, and so I'll be talking about now about weighted least squares control variates. So what we imagine is that we have a sequence of linear approximation spaces. For instance, these could be polynomial spaces. So we imagine these V1, V2, which are all nested. And then they are nested, and in in the limit, they are dense in L2. And we also say that their dimension is M. So the idea, very simple, is to construct the model VK by a least squares on a subspace VMK tensor U using a sampling distribution mu and the memory. So this is what we've been going on about. I'm just giving a practical example of what kind of a model and a fitting procedure could be. And so essentially we define VK as this projection onto the space VMK using memory SK of the gradient of G. And this is the least squares fit weighted, so we do weighted least squares, and then we essentially fit these data points that we have from SK. Note that this SK, so the idea is that VK should kind of approximate the gradient of G at UK, but this is kind of inexact data that we're using here. So I would like to first, yes, draw a bit of draw your attention to the error decomposition that we get. So let me introduce, so this W star K is the best approximation in our linear space of the function that kind of we are targeting at step K, which is the gradient of G at UK. So this is the best approximation. This is the projection of this function. Then WK instead is the discrete projection based on exact data, right? So now we have the WK uses data at UK, but at the same kind of collocation points Yj, and then by just triangular inequality, we have that we can decompose. So this is the error that we have. So our model VK versus our target function here at G, and the error decomposes in the following way. So we have a projection term, which is how well the gradient of G is approximated in our class. This error, of course, decreases as the class gets richer, of course. So kind of this term wants us to pick like an MK, which is big. Then we have a second term, which is the difference between the two discrete projections, the one with the exact data and the one with the inexact data. And the point is that here we fit, yes, with inexact data. So we have that our evaluations are at uj different from uk. And this term essentially wants us to to keep like a small window, because a fresher window leads to less inexact data, right? So actually this term would like us to take an like a sample, like a memory size as small as possible. Now it clearly cannot be that M should be like as large as possible and should be like as small as possible. Like there has to be like a limiting factor. We cannot just take S equals 0. And that's given by the third term, which actually couples the terms sk and mk. And the point is that here we need to kind of, uh, for a given space, VMK, we need enough samples to stabilize the fit and make and essentially to control this term, which is the difference between the true projection W star and the discrete projection with exact data. Right. So with this slide, I would like to kind of convey the message that now we have some parameters to choose, right? There's the model size and kind of the memory size. And we want the model to be big, the memory to be as small as possible, but what are the constraints, right? And so this kind of motivates my small digression now into right? So we need to pick the schedules and K and SK to balance these effects. And so now I'll be digressing a little bit into a review of optimally weighted least squares. And this is from the work from Cohen and Migliorati from 2018. So let's consider a target function psi from gamma to r. So now I'm considering, actually, instead of u, I'm considering like a Hilbert space on one dimension. And then we consider an approximation space Vn with orthonormal basis given by these phi i's. And so given some samples from mu, S samples from mu, we define the projection with exact data, which is given by this pi hat Vm of psi. Again, this is the same kind of weighted least squares that we had earlier, but with exact data now. And so then we have the Gram matrix, which is the inner product between the discrete inner products between the basis functions. And note that here we always have our weighting, the rho and the mu. And this satisfies, of course, since we're taking an orthonormal basis, this satisfies that the expectation of G is the identity. And then we can define this leverage constant, which is this quantity K, which I mean, it's not so important how it's defined, but the important thing is that it depends on our space M and the measure mu. And there is this result, which from Cohen and Migliorati, which says that essentially if, and here is the key, if the sample size, so S over log S, is greater, so it's greater than essentially scales like this K of M and mu, then the Gram matrix concentrates near the identity, and the weighted least squares is stable and near best in expectation. So really, this is given like the inequality that we were looking for. Essentially, we cannot. So given a search space VM and a sampling measure mu, the kind of the smallest sample size that we can get is given by this kind of sampling inequality. We cannot take S too small. It has to be large enough. So now the second key observation is that now, okay, now this K, okay, depends on the space, whatever. If the space, we kind of think of it as something fixed, that for now we're fixing, but we have some other parameter that we can play with, which is the sampling measure. And this kind of also motivates why earlier I introduced our algorithm in the setting where we would like to kind of change the sampling measure compared to the base measure. So now the idea is that we should make this K of M and mu as small as possible by choosing like a kind of the best mu, sampling measure mu. And indeed, yes, so we would like to choose the sampling measure to minimize K of M and mu. And it turns out that there is actually a closed form for the optimal sampling measure, which is the one given here. And remarkably, this gives the best, the kind of the best k that one could imagine, which is actually that it scales linearly with it's actually equal to m, which is the dimension of the space Vm. And notice that indeed this yes, the important thing to notice here is that this optimal measure depends on the space Vm, right? And so the sampling inequality that we had earlier, I introduced the constant k, now becomes this, which if we essentially ignore log factors, it's saying that S should kind of scale linearly with the number, so with the dimension of the space. And this is kind of the best that one could hope for, because of course, to have like some stable least squares, we have to at least have a number of valuations, which is at least the number, the dimension of the of our space. Right, but then also we have a little bit of a Oh, sorry. Before that, actually, an interesting observation is that when we have nested spaces, so Vm included in Vp with so p larger than m, we can actually express this optimal measure. We can express it as the optimal measure of Vp is a mixture of the optimal measure of Vm and this perturbation eta p, and eta p has the kind of the new basis functions that we have added. And so essentially, if m and p are similar, we are in the setting that I showed you earlier, where we had a like the new measure was kind of the old measure, uh, like a mixture of the old measure and a perturbation with that parameter alpha k, which was close to one. And here, close to one means that actually the two dimensions are essentially we're just adding a few basis functions to get to Vp from Vm. Right, and then we have also the notion of a quasi-optimal measure, which is now if we consider a sequence of spaces Vm, which are nested, a quasi-optimal measure is a measure mu, which is space independent, and such that kind of we have almost the kind of the best scaling up to a constant c. We have the best scaling of this constant k of m and mu for all m, right? So I mean the sampling inequality worsens by a factor c, but the scaling with m remains linear here. And a notable example, I mean this kind of course depends on the finding. So the optimal measure kind of always exists, but this quasi-optimal measure is a bit trickier, and so it exists sometimes. And a notable example is in the case of a uniform distribution, and if you take for instance the phi i's to be Legendre polynomials, actually it turns out that the arc sign measure is quasi-optimal. So it's independently of the size, kind of of the polynomial degree of you have always quasi-optimality with constant pi over 2. Right. So now I showed you how to kind of I digress um, into how we do weighted least squares. And so this is a method to kind of fit our model to the past observations. And then we tackle this question of, okay, but given a model and how big the model is, how small can we take the kind of our rolling window in the past to fit the model? And this was the content of the section that we just went over. And now, so let's get to the algorithm, right? And so now the point of the algorithm is, so now how do we choose, this? So the last thing to choose is how big the model should be. And the first idea is just to say, okay, let's pick a model and have m be constant, right? So we have the same kind of search space for at all iterations. And this is kind of the first algorithm that we propose, which is this SGLSCB, so stochastic gradient with least squares control variate with a fixed subspace. And this really goes kind of in the direction. This is just an instantiation of the earlier kind of algorithm, more general algorithm with kind of the model and the fitting. So as I was saying, so we're given a subspace Vm, which is constant during the iterations. a quasi-optimal sampling measure mu, a memory size which satisfies the sampling inequality. Then we have always an initial guess, initial memory, and an initial model. And then for each iteration, we again draw one yk from the measure mu, which is our quasi-optimal measure, independent of the past, evaluate our gradient, and then we do the updates just as we saw in the earlier algorithm, with the difference that now our model is actually this kind of least squares projection of our gradients, right? And also notice that in the case so kind of in the case of actually orthogonal polynomials, this term here is actually is computed exactly and is readily available. This is the constant factor of a polynomial. So in this case, there's no need to modify the memory size S. So essentially, our memory is just a rolling window. So what we do is that at each iteration, we delete the oldest observation and we keep the new observation, and then we update the model, solving again a weighted least squares problem. So indeed, yes. So at each iteration, we have to refit the whole model, resolve the weighted least squares problem. But since our observations aren't changing much, so we only change one sampling point per iteration. Essentially, we can do an efficient QR update of so essentially to make this fitting at each iteration cheaper. Right. So we were able to provide also a convergence analysis of this algorithm. So let me introduce this term DM, which scales like the best approximation of the grain of G in our model space, plus another term which should be thought as just a small perturbation. So this DM really should be kind of the least squares error that we have given our model space. And this follows from the fact that we have a quasi-optimal mu and the sampling inequality is satisfied. Then we introduce this quantity Q, which is the supremum of this Radon-Nikodym derivative. And the theorem essentially goes like this. If the step size, which by the way is constant, I didn't draw your attention to that, but in this algorithm we say we keep the step size constant, and we say that if this is taken small enough, then there exists a gamma such that the error has this behavior. So essentially what we have is that we have an exponential convergence up to least squares error, of course, up to this constant, which involves also this kind of supremum of this Radon-Nikodym derivative. Right. So essentially, I would like to now kind of jump right into some numerics to show you how this kind of algorithm fares. Oops, sorry. Before that, there's an important fact about this gamma, which is that it actually scales badly with with the sample size S, and this is similar to SAGA. So we have that gamma scales like 1 minus log S over S. And actually here I write improvement via error recursion. This means that essentially in SAGA you would have 1 minus 1 over S. But actually I think we with our proof strategy, which is different from SAGA's, which relies on a kind of a Lyapunov analysis. We actually analyze an error recursion, and actually we think that there may be the potential to actually improve SAGA's results using our analysis instead of theirs. Right. So I was saying that I would
Sorry,
like to jump.
Matteo, what is delta here?
So this is a small constant actually. It's a constant. Yes.
Okay.
Yes. All right.
Thank you.
So you're welcome. So right, numerical experiments, actually, as I just said earlier, actually what we are interested in is a PDE-constrained optimization. So what we are interested in is a PDE given in this form, so with some differential operator L, which depends on parameters Y, which are random. And this equation defines our state Z, and the F is the forcing term. U is the control to be optimized. And what we are usually using in our experiments are cost functionals of tracking type, meaning that we would like the solution of the PDE to satisfy, essentially to be as close as possible to some target state, also penalizing a bit the size of the control, right? And so this is the stochastic optimization setting that I presented at the beginning. So the optimal control is of course defined as the argument of this functional subject to the PDE being satisfied, right? So this is why it's PDE-constrained optimization. We have a model problem. This is very simple in 1D. So the PDE actually now is just an elliptic equation with one random parameter with no forcing term. And I mean, the parameter has this distribution, which is not so important at the moment. The only thing is that in this case, if we take the Z target as an eigen function of the Laplacian, essentially we have a closed form solution, so it's easy to compute diagnostics in this case. And we take Vm as the span of the polynomials of degree strictly less than m. And we use the Legendre basis, and we use the quasi-optimal arc sign distribution on -1, right? Because the base measure is uniform. So, and this is how the picture looks. So essentially, we have here the convergence of the fixed subspace algorithm that I just presented for different sizes of the approximation space, right? So if we have a small approximation space, m equals 6, what we have is that we have fast convergence, and then we have stagnation at a high kind of approximation at kind of at high error, because we're approximating just with 6 polynomials, our gradient. Then if we increase the size of the polynomial space, what we have is that we are reducing the convergence speed at the beginning, but then we stagnate much lower, and so on, right? And so this is exactly the picture that I showed you. This is exactly the picture that our theorem predicts. And here comes the idea, of course, right? Because then this is kind of telling us, well, at the beginning, we shouldn't start with a big space, right? We're far from the optimum. We would like a small space to kind of regularize somehow this. We don't want to overfit like very bad kind of data, which is far from the optimum. So we should keep a small approximation space and kind of gradually enlarging its size as we converge. And so the idea we would kind of like we would like to have an envelope of these plots. And this is exactly what we did. So we also proposed the algorithm with an increasing subspace. And so here the key elements are these scheduling functions. So we have a scheduling function for the subspace size at iteration k. Then we have the measure that we have to sample from. So now the space is changing, so also the measure potentially is changing. And so we have the quasi-optimal sampling measure at iteration k, and then this memory size at iteration k always has to satisfy the sample inequality, right? And the algorithm really kind of looks almost the same as the one we had earlier, but with the difference that now we're sampling from the measure mu k, right? And also when we update the memory in the same way, I mean, we have a scheduling function that tells us how far into the past we have to look to get our data. And then the only thing that we have to add compared to the earlier algorithm is that if mu k plus 1 is different from mu k, then we have to do the resampling step, right? So this is why we introduced that resampling step, because in this case, actually, we do need to keep the memory consistent, right? And then we update the model again using the resampled memory. So we were able in this case to prove these results, and this is the following. So essentially, if our error decreases, we have sorry. So this is if the approximation error in the chosen subspaces decreases exponentially. um, so with some rate eta. Then we also define this qk, which is again the supremum of this radionicodym derivative that now it depends on the space, and so we allow it to grow with the space size, with xi which is in 0, 1, and this is actually this assumption is true when a row is uniform, so we have xi equals 0, so actually no growth, and Gaussian we have growth with rate 1/2 when mu k is optimal, right? And if these things are satisfied, then choosing these schedules, so mk grows like the cubic root of k, sk is the space size squared, and the step size is 1 over the sample size, we get essentially a sublinear convergence result, right? Where the rate here depends on the original rate eta. So we have, okay, sublinear but super algebraic convergence with only one gradient evaluation per iteration, right? And so we kind of almost achieve the kind of the starting goal, which was to kind of have a SAGA type, this kind of SAGA type result where we re-achieve the good convergence of gradient descent, or not quite in this case, because we have this root 1/3. But here we have a continuous row, right? So we also have the corresponding results in the case where the approximation error decays only algebraically with rate eta. Again, we have same assumptions regarding this weight qk. And in this case, we choose slightly different scheduling functions, as you see here. But what we get is essentially that we improve. Essentially, this is curious because you see that sk actually is growing like k, and tau k is 1 over k. And so here what we get in our convergence rate, we have the kind of -1. So we have an algebraic convergence rate, but an improved one. We have the -1 coming from which is the standard kind of stochastic gradient decay. And then we have this extra term, which is xi minus 2 eta, which essentially depends on how good. So this is how much we improve exploiting this kind of smoothness of our map, grid G, at the optimal control, right? So now let me go on with the numerical experiments, and going back to our diffusion equation with one random variable. Now, if we have an increase in subspace, what we get is this red curve, which kind of looks like the envelope of those curves that I showed you before. Then here we actually also tried the algorithm with with a constant step size, this kind of variable approximation space algorithm. And so essentially you see that up to a certain point it kind of works, but then at the end we have a decreased convergence rate. What we can beat is SAGA with 20 Gauss points. So here we are comparing with SAGA with the spectrally accurate quadrature, of course. So also in SAGA we're kind of exploiting the smoothness of the map that we're exploiting with our algorithm, and we see that we massively outperform SGD and Atom in this benchmark. So we also tried a little bit of a more complex equation, so problem. So the PDE now is advection diffusion. Just very quickly, we have we have 5 random parameters, and the cost function is always of tracking type. So here we are trying to reduce the size of the solution, and the approximation, sorry. So the approximation space that we choose here is we take a polynomial space with hyperbolic cross design. So essentially we can take an M which is large enough even in 5 dimensions, right? And the sampling measure is the quasi-optimal mu on -1, 1 to the power 5, right? So the point here is in actually I think the key point here is that with our algorithm we're kind of free to choose this VM. I mean, we're very free in the choice of VM. So we're not restricted to a tensorized, for instance, design where we would have a growth of the type m to the power 5. So essentially, we can exploit the kind of the regularity and of our map better. And here we have the picture in this in this setting. So with this example, so we have a similar. So on the left we have the fixed subspace that we have a similar picture as earlier. So fast convergence for a small subspace and kind of but kind of stagnations at a high error and vice versa as we increase the size of the subspace. And on the right, we have actually, again, our variable approximation space, which confidently beats SAGA. Again, here we're comparing with SAGA with with a tensorized Gaussian quadrature with five points and 8 points on each axis, respectively, right? And so we confidently beat with SAGA. This is actually thanks to the improved flexibility that we have in designing our control variate compared to the design of the quadrature of SAGA. Right. So this brings me to the conclusions and kind of if there's one message that I would like you to take away from my talk is really this simple message, which is if the map, essentially if this gradient at the optimal control as a function of the parameter is amenable to approximation. So for instance, it's quite smooth as we have seen that we have in our in kind of PDE-constrained optimization settings, for instance, then we can and we should exploit this smoothness, this approximability, and in this case, our algorithm achieves fast convergence with one gradient per iterate. Right. So this is really the key message. And in terms of outlook, so future work, it would be interesting to consider, for instance, I mean, there's actually many things that one could could do and many ways in which one could extend this work. So for instance, using other approximation spaces, for instance, trying RKHSs for perhaps neural nets. Then it would be nice also to understand what happens beyond strong convexity. So that is, of course, because I mean we kind of consider this very nice case of the strongly convex setting, which is relevant, but it would be nice to to see what happens beyond that. And then actually very interesting. So actually in the algorithm that I showed you, it would be nice to have an adaptive way to kind of build and construct the optimization, sorry, the approximation space as the optimization goes on. That's actually a very interesting direction, and also it would be interesting to see if these kind of exploiting kind of the smoothness with respect to parameters of the gradients to improve convergence could actually have. So I think, okay, I think my time is almost up and I'm actually done. So these are my main references. So we have the work from Quen on optimal weighted least squares, then the SAGA work, then an application of SAGA to the PDE-constrained optimization problem by Fabio and Matteo Martin. And finally, I would like to draw your attention, if you're interested, to our preprint on arXiv. And yeah, I'm done. So thank you for the attention, and I'm happy to take questions if there are any.
Thank you.